Hey everyone, my name is Alex, and I am a first year PhD student doing research in distributed systems and security. I'm here to talk broadly about the current state of VR and privacy. So, first, let's start with why is VR security important? Several corporations, notably Facebook, is trying to push a metaverse social platform where users share a cyberspace and interact with each other. This now opens up a lot of personal attributes that are now exposed to others as opposed to the web. Imagine having a metaverse conversation with another user you find online who wants to infer as much as possible. What can they infer? So, in exploring the unprecedented privacy risks of the metaverse paper, they observed four different types of attackers. Type one is the hardware adversary, basically the VR headset that can control firmware or the OS if the headset has one. This is the most powerful adversary and can observe raw sensor data from the headset. There is type two, which is the client adversary, the VR app that runs on the VR headset. The adversary can use any APIs to call into the host. It's basically the same privilege as an app you download to your computer. The server adversary is where if any data is being processed on the network, that is typically sent as a result of the client adversary. So if the app uses online components, it will send stuff on the network. Finally, the user adversary is the weakest model where it can only observe you and doesn't have any special privileges. An example would be a user observing you through an online metaverse chat. This is a visualization of the previous slide. The VR device is running in the Unity application, which sends network data to a server, which can be observed by another user online. So what can the attackers observe? They can observe the geospatial telemetry, so how the headset slash controller moves over time. Privileged attackers can see device specifications of your VR headset. All attackers can geolocate users either by observing the IP if they are privileged or observe network latency side channels for an observing user. Lastly, they can observe how users react to stimuli visually or through audio. The paper creates an escape room style game and asks participants to solve puzzles, which were disguised to infer attributes of the user. For example, one of the puzzles required the user to squat. You could infer the depth of their squat to their physical fitness. You could also infer a user's VR refresh rate, even unprivileged, by observing their perceived motion differences by having them read text. Here are the results and how accurate the results were. This is just a subset of the table they collected. They could accurately determine most of the user's attributes. I also box read some attributes like age and income, which were inferred by primary data points. They used an ML model to predict these based on the primary data inputs they got from the experiment. So now that we identified how much can be inferred about us, how do we protect ourselves in the metaverse? Each personal attribute risks de-anonymizing us. Furthermore, the information inferred from the experiment could largely be done in a non-privileged setting, so any user observing could have inferred that much. The question is, how do we reveal minimal data without affecting the user's VR experience? The problem is similar to if a company like Facebook wants to do analytics on its users, but users don't trust Facebook to de-anonymize them. How can Facebook query users to perform helpful analytics but ensure that no one user is de-anonymized? How about adding noise to our data, but how much to ensure that we are anonymous and Facebook can still do meaningful analytics? So this is where differential privacy comes in. For any two adjacent data sets D1, D2, which differ by one data element, the probability distribution of some algorithm A on D1 is bounded by e to the epsilon. In other words, let's say you are in the data set D1 and D2 represents the data set without you. The probability of algorithm A, which is a query or algorithm that processes the data, is bounded by e to the epsilon times the probability of A computing on D2. If epsilon is zero, the probability distribution is the same for both D1 and D2, which implies that U existing in the data set or not doesn't change the properties of the results of A. Epsilon represents how much privacy is lost. Another important property of differential privacy is that they compose. If I have multiple algorithms that want to compute on the dataset X, the epsilons simply add up so that we can have multiple queries bounded by some target epsilon privacy budget. We can apply this to VR by adding noise to attributes that give us epsilon differential privacy. Another paper does exactly this. This paper describes a Unity plugin called MetaGuard, which enforces epsilon differential privacy. For example, voice pitch and distance between pupils, we can add a constant noise offset, which corresponds to an epsilon privacy loss. For wingspan and height, this wouldn't work. For example, if we want to touch the ground, we could only go down to ground plus offset. Not only does that reveal the offset and reveal the noise to the attacker, it also affects user experience like picking up an object on the ground. This can be solved by doing a multiplicative offset instead. Boolean attributes like a user's dominant hand can be differentially private by using a randomized response. One example is if a user flips a coin and it lands heads, they will tell the truth. Otherwise, they flip another coin, heads being true and tails being false. The user can adjust their privacy budget trading off user experience for more noise added. Here is the interface for MetaGuard. On the bottom, you can adjust your privacy epsilon budget. You can also toggle different attributes you want to add noise to. I demonstrate toggling on height, which adds noise to my current height. I also toggle handedness, which randomizes my dominant hand by mirroring the same. So MetaGuard is a plugin which integrates with the client app, but what about type 1 and type 2 adversaries where the app itself or the firmware can be untrusted? I looked into whether there has been research into hardware security within a VR headset. Some defenses against type 1 and type 2 attackers would be hardware support to protect sensor data from both client programs and firmware using confidential computing, like Intel Software Guard extensions. Apple does something similar by processing fingerprints or any sensitive data inside secure processors called secure enclaves. However, it seems like there hasn't been any type of research done in this area. This concludes my presentation. Thank you.